Welcome to section 5.2, where we explore inverse functions. In part 1, we will talk about the basics of inverse functions, such as what is an inverse function and how can we find one algebraically. We will also explore what it means for a function to be one-to-one. If you take a look at this graph here, we can see that we have three functions graphed. The first one is f of x. The second one is its inverse, f inverse of x, written as f to the negative 1 of x and said f inverse of x. The last function that's graphed here is this dotted line, which is simply the line y equals x. It is just y equals 1x plus 0. It has a slope of positive 1 and a y-intercept of 0. So this is our notation. And a couple cool things about this are f and f inverse are actually reflected about the line y equals x, or you could say reflected over the line y equals x. In fact, any function and its inverse are actually reflected about the line y equals x, which is really cool. That leads to the idea that if a certain coordinate point is on the original function, then its inverse, or just swapping the two numbers, is actually on its inverse function. So I wrote that out as if the coordinate point a comma b is on the graph of f of x, then the inverse b comma a is actually on the graph of f inverse of x, which is pretty cool. So let's take a look at that. Some bad examples would be 0, 0, and 1, 1, since they're the same backwards and forwards. However, we can actually take a look at this coordinate point here, which is on the graph of f of x, the original function, and it's the coordinate point 2, 4. Then the coordinate point 4, comma 2 should be on the inverse of f, which it is. Right here we can see the coordinate point 4, 2 is actually on the inverse. So that's a neat algebraic idea, and it actually flows right into how we algebraically find the inverse of a function. Since a function and its inverse graphically are actually a reflection about the line y equals x, and the inverse coordinates are on the inverse graph, what we're actually going to do to find the inverse algebraically is swap the coordinates. We're going to swap x and y. So really, this says y equals 1 minus 2x over 5. So I'm going to just rewrite this. I haven't found the inverse yet. I haven't taken any steps to that yet. I'm just simply rewriting f of x as y. Then what we're going to do to find the inverse is we're going to swap x and y. So instead of writing y equals, I'll write x equals. And instead of writing 1 minus 2x over 5, we'll write 1 minus 2y over 5. So our next step looks like this. We've taken the first step towards finding the inverse, since the inverse function is the reflection about the line y equals x, and the coordinates are swapped, so we swap the coordinates. Then, in order to find the inverse, we need to solve for y, since the function is y equals. And right now we have the inverse function in terms of x. We want it y equals. So our next step is to solve for y. So we can multiply both sides by 5 to get 5x equals 1 minus 2y. Then we can do a couple different things. I'm going to actually add 2y to both sides to keep things positive, and then subtract 5x from both sides. So I'll add 2y and subtract 5x. Then the final step is going to be to divide everything by 2. So instead of writing y, since this is our inverse function, I'm going to write it as f inverse of x, and it equals 1 minus 5x all over 2. I've graphed our original function, which is in red, the inverse function that we found in blue, and also the line y equals x, which is dotted. Now, sometimes it's hard to visually see a reflection about this line. Sometimes it's a little weird and not like exactly what we think it might look like. So that's when I actually like to take a look at some coordinate points, just to double check that we did this correctly. So what I'm going to do is take a look at the tables for each one of these, and then we can clearly see that we have a couple coordinate points. So on our original function, we have the coordinate point -2, 1. And one other coordinate point that we have is 0, comma, 0.2. Then I opened up the table for our inverse function, the blue function, and we can clearly see that the inverse of -2, 1 is on this function. It's the coordinate point 1, comma, -2 right here. Now, while one coordinate point, working doesn't necessarily guarantee that we did everything right, we can keep looking at other coordinate points, but it is really cool that you can graph these on Desmos and see what a reflection would look like about the line y equals x. Our next example, g of x, is a rational function, and again we want to find the inverse. So we said that our first step is to simply rewrite our function so it looks like y equals, instead of function notation, g of x. All right, in order to find the inverse, we need to swap x and y. We need to invert the variables. So I will replace x with y and y with x, so our function now looks like this. This one's a little bit different because now we have two y's here, whereas over in this f of x, we only had one of them. So this is actually the equation of our function, our inverse function, g inverse of x. However, it's in the terms of x equals, and we want it as y equals since that's how we write a function. So what we need to do is solve for y. Now there's two y's here, so we need to get them all on the same side. Our first step, much like over here, is going to be multiplying by the denominator so we can get rid of the fraction. So we're going to multiply both sides of this equation by the denominator 1 minus y. When we do that, we're left with 2y on the right-hand side. On the left-hand side, what I'm going to do is distribute the x through. So we'll have x minus xy. Now we have y's on both sides of our equal signs, but at least we're done with having a fraction. The next step is going to be to get all of our y's on one side. And in this case, to keep things positive, I'm just going to add xy to both sides instead of getting all the y's on the left, since that would make a lot of things negative. It's really up to you with what side you'd like to get these things on. Now we have all of our y's on one side. What we can do to get the y's in one place is to factor the y out. When we factor the y out, we'll be left with y times the quantity 2 plus x. Then we can get y by itself if we divide both sides by 2 plus x, or x plus 2, whichever order is fine. So what we have is now our inverse function in terms of y, or actually in terms of x, we have it as y equals. So we have g inverse of x equals x over x plus 2. I'm just switching the order of the denominator. So we have found our inverse function. Let's take a look at them on Desmos again. These ones look really weird, so I decided to just take a look at their tables instead. So I messed around a little bit with the inverse. So here's our original function and here's our inverse. And the way that I got to these tables is I hit this little settings tab and then click the little thing that looks like an XY chart. So we have a couple coordinate points here. This is the coordinate point -2, comma, -4/3. And then so what I did here is I typed in -4/3 for x and made sure I got out -2, which we did. So we have this inverse coordinate point here, which works. Then -1, -1, and 0, 0 are their own inverses, so they're on each graph. Those are some intersection points. Then we have this coordinate point, which is hard to invert since we can't plug in undefined. But we can clearly tell why 1 is undefined here. It's a vertical asymptote. Therefore, it's going to actually be a horizontal asymptote of our function in blue, which it is. The line y equals 1 is a horizontal asymptote for our inverse function, where x equals 1 is a vertical asymptote for our original function. They're swapped. This last one I did by hand. So 2, comma, -4 is a coordinate point on our original function, and its inverse, -4, comma, 2 is a coordinate point on our inverse. So just some neat things that you can play around with on Desmos to make sure that you did things right. In this third example here, we'll find the inverse and also write out the step-by-step directions that we've only since talked about and not written down. So in order to find the inverse, the first thing that I like to do is just simply replace f of x with y. We haven't really taken any steps toward finding the inverse yet, but it just helps me to see y instead of f of x. So I wouldn't really even call that a step. We just rewrote. Then, in order to find the inverse, we're going to switch x and y, since algebraically that's how we find the inverse. That will look like writing x equals 3 times the square root y plus 2 minus 5. Then our final step, since we already actually have our inverse function here, we just don't have it written in function notation as y equals, what we want to do is then algebraically solve for y. Now this can look like a lot of different things. We saw in the former two examples that we had two different fractions, and each one of them had a slightly different process depending on how many y values there were. In this case, we have to first add 5 to both sides, and then we need to divide everything by 3. Since y plus 2 is now under a square root, what we want to do is square both sides. So once we square both sides, we'll be left with y plus 2 equals x plus 5 over 3 quantity squared. Then we want to subtract 2 from both sides. So I'm going to rewrite this with the y on this side and have y equals this, x plus 5 over 3 quantity squared minus 2. The very last step is to simply replace y with the correct function notation, which in this case is going to look like f inverse of x. So we will simply replace y with f inverse of x. We have discussed algebraically in this video that in order to find the inverse of a function, we swap x and y. Therefore, any coordinates that are on our original function, the inverse of those coordinates are on our inverse function, swapping x and y. It would only make sense then that the domain and range of a function and its inverse have a special relationship and are probably swapped or inverted as well, since domain is x values and range is y values. What I have here is a function and its inverse. They're both rational functions. Let's take a look and find the domain of each, and then take a look at what the range is by graphing. So the domain of our original function is all x values except -2. Therefore, we can write that from -2 to negative infinity to -2 union -2 to infinity. And the domain of our inverse function is all x values except 0, so we can write that in a similar way. So we found the domain. Let's take a look at what the range would be. But before we actually get to the range on Desmos, I want to just point out what the asymptotes are. That's another good thing to see the relationship between. So we can see that in this original rational function here, we actually have a vertical asymptote where x is -2, since x plus 2 does not cancel out top to bottom. We do not have any holes in this graph. So our vertical asymptote is actually the reason our domain is restricted, and our vertical asymptote is the line x equals -2. Over here, our vertical asymptote is the line x equals 0 for the same reasons. Next, we want to take a look at the horizontal asymptotes, if we have any. Remember, the rules for horizontal asymptotes are looking at the degree of both the numerator and the denominator. So the degree of our numerator here, n, is actually 0 because there's no x up there, and the degree of our denominator is 1. So since n is less than m, our horizontal asymptote is the x-axis, the line y equals 0. In our inverse function, our n value and m value are tied at 1. Therefore, the horizontal asymptote is the ratio of the leading coefficients. Be careful with the order things are written. The leading coefficient in the numerator is actually -2. Leading is kind of misleading, if you will. So this is -2 over 1, which is the line y equals -2. Take a look at the relationship between the vertical asymptotes and the horizontal asymptotes of a function and its inverse. Note that the vertical asymptote of the original function is actually the horizontal asymptote of the inverse function, obviously swapping x and y. Same relationship applies going from horizontal to vertical asymptotes, which is pretty neat. And this all works out algebraically because of that special relationship between the x and y coordinates of a function and its inverse. All right, let's take a look at Desmos to check out the range. Our original function is in blue, while the inverse function is in orange. So we can clearly see that the range of the blue function, it looks like if we zoom out just a little bit here, the one y value that we're not taking on in our blue function is the horizontal asymptote, which is y equals 0. So our range is all y values except 0, since we're never hitting the x-axis here where y is 0 on our blue function. The inverse function in orange is very similarly shaped. However, we are not taking on the y value of -2, which is the horizontal asymptote there. And if we zoom out, we can clearly see that we're never hitting those horizontal asymptotes. That's why they are asymptotes. So our original function, we hit all y values except 0. Our inverse function, we hit all y values except -2. I've completed writing the range. We can see that the relationship between a function and its inverse here is what we'd expect with the domain and range as well. So the domain of the original function is the range of its inverse, and the range of the original function is the domain of its inverse, which is really neat. And again, that's the relationship between a function and its inverse in terms of x and y. They're inverted. A big idea when discussing inverse functions is the idea of a function being one-to-one. A function is one-to-one when its inverse is also a function. In order to see if a function has an inverse that is also a function, i.e. to see if a function is one-to-one, what we can do graphically is see if that function also passes the horizontal line test. A horizontal line test is just like a vertical line test. So we've already discussed that a vertical line test is used to make sure that a relation is a function. So we can clearly see that the circle, not a function. It fails the VLT. But in order to see if a function would have an inverse that's also a function, we can see if that function passes what's called the horizontal line test, or the HLT. If we can draw a horizontal line and it intersects only once, then that function also is one-to-one, meaning its inverse is a function. Note here that this quadratic, this parabola, y equals x squared of some sort, is a function. It passes the vertical line test. However, its inverse would not also be a function because it fails the horizontal line test. Therefore, it's a function, but not a one-to-one function. Whereas this circle here, not even a function. This last function here, this green one, not only passes the vertical line test, so it's a function, it also passes the horizontal line test. Therefore, it's a one-to-one function, meaning that its inverse is also a function. To end this part 1 video, we'll take a look and answer the question, are these functions one-to-one? So we know that both f and g of x pass the vertical line test because we're calling them functions. However, we need to see if they pass the horizontal line test and are invertible functions to see if they're one-to-one. So this first one, we can either graph it on Desmos or simply sketch the graph. I will just graph it on Desmos to make it a little bit simpler, and we can sketch the graph to number 2. We can see that this function is a pretty simple rational function, and it has that general curved shape of a rational function. It does pass the vertical line test, even though it does get extremely steep by our vertical asymptote, x equals 0. And also it gets incredibly flat by our horizontal asymptote, y equals 0, as we zoom out a little bit. However, we do pass the horizontal line test, because if we drew a horizontal line, even though this looks like it's becoming a horizontal line, it never is exactly horizontal. It's always approaching the line y equals 0. So this is actually an invertible function. It passes the horizontal line test as well, meaning it is one-to-one. In number 2, we know the general shape of a quadratic. And since it's negative, it's going to be opening down. The x plus 2 inside the parentheses means that the vertex is over 2 units from the origin. So to sketch it, it looks like this. That's not an exact sketch. It's not perfect by any means. However, we can clearly see that although this is a function and does pass the vertical line test, it's clearly not a one-to-one function because it doesn't pass the horizontal line test. We could draw multiple horizontal lines through this parabola and it hits more than once. So therefore, although g of x is a function, it's not a one-to-one because it doesn't pass the HLT. Therefore, although it does have an inverse, its inverse would not be a function.